everybody. We are going to continue talking about hypothesis testing. Last time we talked about sampling distribution of the mean, and this should look somewhat familiar to you. This is a normal distribution using z-scores. What we talked about last time was the standard error and that average difference or the expected difference that we get from a population and a sample. And remember, with hypothesis testing, we're taking a sample or sample data and we're seeing how different it is from a population and deciding whether that sample data represents that population or whether it's significantly different. And if it is, then we go ahead and say, well, if this sample of rats, for example, who are given a growth hormone, if they are significantly larger or heavier than the normal population of rats from which they were selected, given that they were given the hormone, then we can conclude, if we have a large enough statistic, that hormone is effective, because we can go ahead and say this sample is probably reflective of the population. So we're using sample data to make inferences about a large population. And in this first example that we're going to be talking about, we're going to be comparing a sample to a population. So what we're doing when we do hypothesis testing is we're focusing on the difference that's obtained between our sample mean and the population mean, and comparing that essentially, or pitting it against the difference that's due to chance. We'll talk about the null hypothesis in just a minute, but the difference due to chance is just basically that mess on the bottom of the equation that I've been talking about. It's that standard error. It's that the difference that we expect, the variability that we expect naturally, that could just essentially be anything. Individual differences, it could be just flukes in the data. Hopefully we clean our data and don't make mistakes, but it could still be, it's just error. It's just, natural variability in the data. Here's one way that we can determine how large our difference is compared to the difference due to chance. You'll remember the z-score from 205. We have here the normal distribution and the probability associated, well, it's not listed, but you can look it up, the associated probability with each of the z-scores. Today we're going to be talking about the region of rejection and what that means. It's very tricky until you get it. And once you get it, you're like, well, that was easy. But it might take you a while to get there. So we're going to be talking about the region of rejection and what that means. So if we use the z-score formula, this top part here is the difference that we actually get. So it's like those group of rats. We take, say, 50 rats from 100 rats or 200 rats, whatever, in a population, and we give them a hormone. And we let them grow up for a little while and see if they weigh significantly more than those other rats from the population weigh, or if we know the population mean for rats and what they normally should weigh without a hormone, how much different is our sample mean from our population mean? If it's pretty big, that's good if we want to show that our hormone is a growth hormone and it's working, but we have to still beat this out. This is the natural variability and the way that the sample would differ from the population mean anyway, and just how samples differ and numbers differ and just mess in our data in general. So we have to make sure that this is large enough that we can't say that this is really what's happening. We can't say that it's just chance. So here's our population mean mu, and we're going to be comparing our sample mean to that. And it's really easy, as I talked about last time, it's relatively easy to get, by chance, a sample mean that's close to the population mean. It's just going to happen. It's going to be easier to do that. These outlying scores, if you recall the graph that I did last time, there's only 1, 2, and 1, 8. Those were the outlying scores. Granted, there weren't a whole lot of means, but still the idea was those were the outlying scores. There was only one of each, and they were the least likely to occur because of the unique combination of the way that I was drawing the samples in groups of 2 from that 4-score population. Anyway, so as we get farther and farther out in the distribution, the tail of the distribution, either way, we can start talking about being extreme scores. Now, if you recall from z-scores, 1 standard deviation, 2 standard deviations, once we get around 2 standard deviations, we get to say essentially something is starting to become extreme. It starts to look a little, maybe not suspicious in a bad way, but maybe there's something really going on here. Maybe this sample mean is substantially different enough from the population that we can conclude that maybe there's something really going on here. So we're always comparing our real difference that we get compared to the difference that we would get by chance. The larger the statistic that this gives us in this case, we could have F's and T's and chi-squares and R's, all those different statistics that we'll talk about or have talked about. But we're going to start with a Z because it's familiar. Once we work our Z formula out, how the farther out our Z is in either end of the distribution, the more extreme it is and the more likely we can say, well, it's very unlikely that this was due to chance alone. And we're always fighting against chance. If you think about science in general, we're always trying to disprove that it's not true. And that's difficult to do. So we're always against essentially the idea that it's not there. So our evidence will pretty much be rejecting the idea that it's just chance alone. And if it's not chance alone, then that leaves the alternative, which is that it's probably a real treatment effect, that there's something really happening there. So if you look at this, the region of rejection is an area of the curve, essentially, and it's set apart by what's called a critical value that is determined by what's called alpha. And that's a probability that we decide as researchers, and I'll talk about that in a minute, we decide how far out in the distribution are we willing to go? Are we going to insist that our statistic be? Is it going to be super huge? And are we going to put it way out here so it's nearly impossible to get it? Or are we going to put it, maybe make it a little bit easier to get? Hopefully that makes sense to you going farther and closer out. But remember, it's easy to get something right here. So we don't want to make our rejection region really, really easy. Essentially, we want to come out here and we want to be able to reject the idea that our data are just false. And that's what we're trying to do. So if we get into the region of rejection, this is our magic area on either side, our magic area that we can say, yes, we have rejected the idea that our data are false, that they are just by chance, this part of the equation essentially. And we are saying that this wins out, and we have enough of difference that we can decide, in fact, this is actually true, or most likely true. Again, it's probabilities, so the region of rejection on either side here is made up of scores, whether they're Z's or T's or R's or whatever they are. They're scores that are very unlikely to occur by chance. That is, and we'll talk about this next, they are very unlikely to occur if the null hypothesis that they're chance, basically, is true. So we're looking for something that's if we make it this far, if we get a big enough number, then we can say we've made it into a region of rejection, and we can reject the idea that it's chance and say, yes, I have a real treatment effect. So that's the idea of the region of rejection. And that is, again, decided by alpha, which we'll talk about in just a second in the next video. But real quickly, I've drawn it this way here because alpha is a probability, and it's the probability of essentially, this being chance. And we want it to be, or the finding being chance. And so if we take a one-tailed test, we put all of our probability on this side. If we want, for example, a directional test that says, the rats are going to weigh more in the sample, then we go ahead and make all the probability over here. But better to do is to do a two-tailed test where we take that alpha level and divide the probability in half, and so that, say, for example, our growth hormone accidentally makes the rats puny. It, in fact, somehow has a reverse effect and doesn't work with the way we want. And in fact, it works the opposite direction. Well, if it just falls below the rejection region, then that's okay. But what if it's significantly lower? What if they significantly get tinier? What if these rat pups never develop? Well, we want to know that too. And so it's always good to cover your bases. And I always tell people it's good to have a directional hypothesis, but it's good to do a two-tailed or non-directional hypothesis test. That way, just in case you're wrong, you are testing both directions. Because if this way you get into the significance and you can say, yay, I have a statistically significant difference, then that's great. But if you only have a one-tailed test, then you won't be able to say that it's significantly wrong in the opposite direction. All this would just mean it's all chance, and there's no effect. But if you have the opposite effect, then you want to make sure that you can show that that's significant as well. Hopefully that would never happen, but it has actually happened a couple times. I'll give you some examples in class. All right, so again, the region of rejection is based on our alpha level, which I'll talk about in a second, but I just wanted to talk about it. It is made up of scores that are unlikely to occur by chance. There are ones that are far away from the mean. There are ones that are in the outlying tails of the distribution, and they are therefore very unlikely to get. And if this is our null hypothesis distribution, that is, we do the entire experiment or study with a treatment that is completely ineffective, or when there is no relationship between the variables, or there's nothing going on, it really is just chance, you're still going to get some extreme scores, but we want those scores to be extremely likely to get if it's by chance. So I know it's confusing, we'll talk about it more in class, but this is hopefully a good introduction for you. And that's the difference between a one-tailed and a two-tailed test. Not the same thing as a directional hypothesis. This is called a directional and a non-directional hypothesis test. That's a picky little point, but I'll talk about it a lot again when you guys have questions. If you have a question about it too, write it down and bring it to class and we'll clarify it. Okay, next I'll be talking to you about the 4 steps of hypothesis testing, and I'll make sense of this alpha thing, and hopefully it'll all become clear and you'll see the light. If not, no big deal, we'll talk about it more in class.